All right. Welcome to the forum on robotics and control engineering. My name is Tansel, Yucelen, and I am an assistant professor at the Department of Mechanical Engineering of the University of South Florida. At my university, I am also the director of Laboratory for Autonomic Control, Information and Systems, or shortly LACES. With the support from my university, I am very proud today to host Dr. Ilya Kolmanovsky from the University of Michigan to participate in our live seminar series on control systems through the FoRCE. FoRCE is dedicated to provide free, high-quality outreach events and online seminars to reach broader robotics and control engineering communities around the globe. To support our mission, we periodically invite distinguished lecturers like Dr. Kolmanovsky to give talks on recent research results related to robotics and control engineering. As such, the FoRCE aims in connecting academicians and government industry researchers, practitioners with each other through cross-cutting research and education discussions. We cordially hope that you will enjoy all the FoRCE events and find them highly valuable to your own research interests. I am almost done, but let me mention a few words about WebEx before I formally introduce Dr. Ilya Kolmanovsky. During the presentation, we are all muted. Please ask questions after the presentation, and you can do this simply by unmuting yourself. And also, session is being recorded to be posted on the FoRCE website. So if you do not wish to have your voice included, you can use the chat. You can send your questions directly to me, and I can read them to Dr. Kolmanovsky. Once again, I'm very proud today to have Dr. Ilya Kolmanovsky. Basically, Professor Kolmanovsky has received. All right. Professor Ilya Kolmanovsky received his PhD degree in aerospace engineering in 1995, his Master of Science degree in aerospace engineering in 1993, and Master MA degree in mathematics in 1995, all from University of Michigan, Ann Arbor. He is presently a full professor with tenure in the Department of Aerospace Engineering of University of Michigan. His research interests are in control theory for systems with state and control constraints and in control applications to aerospace and automotive systems. Prior to joining University of Michigan in 2010, Dr. Kolmanovsky was with FoRCE Research and Advanced Engineering in Dearborn, Michigan for close to 15 years. He is a fellow of IEEE, a past recipient of the Donald P. Ackman Award of American Automotive Control Council of 2002 and 2016 IEEE Transactions on Control System Technology Outstanding Paper Awards, and of several awards of FoRCE Research and Advanced Engineering. He is also named as an inventor of 98 United States patents. So, for all of you here live for the presentation of him, first I would like to thank Ilya for participating in our forum. And Ilya, whenever you are ready, please go ahead and start.
Okay, excellent. Thank you very much for the very kind introduction. Are you able to see the slide on the screen?
Perfectly.
Okay, excellent. Then let me begin. So first of all, I'm very pleased with this opportunity to say a few words about reference governors for control of systems with constraints. Before I begin, I would like to acknowledge Elmer Gilbert, who has introduced me to these ideas many years ago, and also my collaborators, whom I do not mention by name, but they are co-authors on joint publications that we wrote, and of course many others who have contributed to this topic over the years. So, reference governors are schemes for dealing with constrained systems. And in constraint control, the objective of the control design is to generate the control signal U to not only track the reference commands R of t by chosen performance variable Z of t despite disturbance uncertainties W of t entering the plant, but also satisfy requirements that limit certain other outputs called constraint outputs to the given set Y for all future time instants. for all time instance. Examples of constraints include actuator range and rate limits, safety and comfort limits, as well as obstacle avoidance requirements, which is a type of safety limit as well. Now, from the application standpoint, the importance of effectively dealing with constraints is increasing. This happens for a number of reasons. First, many systems are downsized. For instance, recent trends have been that engine displacement volume in passenger cars has been decreasing. And there is also a larger number of missions currently involving smaller satellites, such as CubeSats. Such systems, such downsized systems, tend to operate closer to constraint boundary and are more likely to violate constraints. Moreover, existing systems are increasingly pushed towards the performance limits, so the same situation emerges. To deal with constraints, effective controllers must be nonlinear and often predictive. In fact, a popular technique for dealing with constraints, and it's also an effective technique for dealing with constraints, involves the use of model predictive control. In MPC, you generate a feedback law by the first move of the optimal control sequence obtained as a solution to a constrained optimal control problem. The type of the control problem, MPC problem that you might pose is given here on a slide. And if you formulate it in an appropriate way, for example, with terminal set constraints, you can guarantee that constraints will be satisfied for future times if they are satisfied at time 0. Now, here's a different type of a situation where you already have a nominal controller designed, which provides satisfactory performance and pretty much does everything you want except for handling the constraints. In such a case, you may not want to replace this nominal controller by an MPC controller, but you might augment it in some way to help it cope with constraint violations. One such scheme for augmenting the nominal controller is the reference governor. And what the reference governor does, it looks at a command which is provided to the system, and it modifies it if it becomes necessary to do so to avoid constraint violation. So this device remains inactive. So the V of t, the output of the reference governor, is equal to the set point if no danger of constraint violation occurs. And if there is a danger of the constraint violation, it will try to minimally modify the command that is fed to the nominally designed closed-loop system. One property of such schemes, or such schemes should have, is that they should be easy to implement and have fairly low computational footprint. Before I describe how we construct reference governors, let me show by example what they actually do. This is an example of a double integrator converted to discrete time. And we have constraints on position, velocity, and acceleration, which is the control input in this case. The nominal controller is of proportional plus derivative type. If we supply a command R equal to 0.5, we could see that the output of the system tracks this command. This is the output is the position. But then if you look at the control input and on velocity, they violate constraints. If you now replace the command by the output of the reference governor, and as we will see shortly, the reference governor is a feedback law that depends on a previous value of its output and on a state. Then this is what happens. The command, the step command, which goes to 0.5, is replaced by a gradually changing command. So this dashed black line is the output of the reference governor, and so it builds up slowly towards the reference. And the effect it has on the system is that it slows down the system response, as shown by the blue solid line here. And as compared to the red dotted line, this is the original response without the reference governor. But as an outcome of this slowdown, the constraints on the velocity as well as on the control input are strictly enforced. Here's another little bit more complicated example. This is a single degree of freedom spacecraft with flexible appendage, and we are interested in changing the orientation of the spacecraft without causing too large deflections of the appendage. So the constraints here are on appendage deflection, basically the model coordinate of the first mode, as well as on actuation input. The nominal control here is the proportional plus derivative feedback on the orientation. And so what you can see if you apply this nominal control, that if you apply large or you demand large change in orientation of a spacecraft, the constraints on the deflection of the appendage and on the input get violated. And in fact, the margin by which they are violated depends on the size of the commands that we are passing on to the system. Now here's the response with the reference governor. And what you can see is that the reference governor changes the steps to the dashed red lines. And so the command is slowed down and constraints are strictly enforced. And as you can see, the amount of the slowdown depends basically on the reference size. So for larger references, we have to slow down the reference more to be able to cope with constraints. Okay, so now as you can see what the reference governor kind of does, the question is how does it do it? And the basic idea is fairly simple. What you do is that you compute the reference command or the modified reference command so that if constantly applied, it would not lead to constraint violation. Here's an example of a system with a static gain 1, to which we apply a step input command. So the constraint here is chosen so that the set point is exactly on the constraint boundary. And as you can see, the output tracks the set point, but because of the overshoot, it violates the imposed constraint. So what the reference governor might do is that it might scale down this reference and apply a smaller command, which is just enough to avoid violating the constraint due to the overshoot. Now, this satisfies constraints, but of course it does not reach our target set point. So what happens is that at a future time instant, and you can implement the reference governor in discrete time, so this can correspond to the future sampling time instant. At the future time instant, you can look at your current state and you can find a way to advance the reference a little bit more towards your original command without violating the imposed constraint. And you can repeat this process at future time instance, gradually building up the reference towards your original command without violating constraints. So this is a basic idea. And now how do we do this a little bit more formally, and how does it look like in terms of the equations? So the key artifact in constructing the reference governor is the safe set. And the safe set can be defined for continuous time systems. It can also be defined for discrete time systems. It can be defined for systems that are linear or nonlinear. So here is an example where we define the safe set for a nonlinear discrete time system. And it's really the set of all constant commands and initial states, such that if we apply the command and we start with this initial state, the subsequent response, the output, satisfies the constraints for all future times. And if your system happens to have parametric uncertainties and disturbances, then this property must hold for all parameter uncertainties and disturbances, also satisfying suitable conditions. All right, so here's how the simplest so-called scalar reference governor is defined. It's defined by a solution of optimization problem where you try to maximize kappa, subject to a couple of constraints. And you can view the reference governor as given by this equation in two ways. You can view it as a linear filter with an adjustable bandwidth parameter kappa, where kappa is between 0 and 1. You can also view it as an interpolation between the previous value of the output, v of t minus 1, and the current value of the command. So if kappa is equal to 1, then v of t is equal to r of t, and you pass the command to the system unfiltered. And if kappa is equal to 0, then the reference governor holds its output at a constant value, and this is essentially an extreme constraint avoiding action. So what you try to do is to choose this kappa as large as possible, so that v of t is as close as possible to r of t, subject to the constraint that kappa is between 0 and 1, and the pair consisting of updated command v of t and x of t is safe. And by safety here, we require that it belongs to a set P, and that set P is a subset of O infinity. Now, why we don't use O infinity here is that in many cases O infinity is difficult to compute, and it also may have quite complex representation. While if we choose for P a simple set that simply represents it, for example, polytope with a few faces, so an ellipsoid, then this is a very simple optimization problem to solve. I'd like to mention that the set P need not be invariant. So if this problem is not feasible, you can set kappa is equal to 0, and the typical response properties of the reference governor that I'll talk about later, they actually hold under this infeasibility handling mechanism. So how do you obtain P? There is a number of offline procedures available. And the simplest case, if your model happens to be linear and constraints happen to be affine, then a set P is a polytope typically, and it's something that's fairly easy to compute. Additionally, there is various procedures available for redundant and almost redundant constraint elimination that allow to systematically simplify representation for this set P and lower computational complexity of the reference governor. Now, if you happen to work with a nonlinear system or with a linear system, and you have a Lyapunov function or ISS Lyapunov function for the closed-loop system, then you can use constraint admissible sublevel sets of such functions for your set P and for your reference governor implementation. Next, if you happen to have a simulation model or experimental system, and so there is the only thing that you basically can do is to simulate or run an experiment, and you can do this for different commands and for different initial conditions. Then you can apply machine learning techniques to find classifier that separates safe pairs of commands and initial conditions from unsafe pairs, and you can use a sublevel set of that classifier for your set P. And finally, there is a variety of response bounding and approximation techniques that can be used in such cases. Let me talk about, in a little bit more concrete details about the simplest case, what happens when the model is linear and also the constraints are affine in the output. In this particular case, we are going to assume that the matrix A is sure, so the system is stable, which is a reasonable assumption since typically the reference governor is applied to closed-loop systems. Now, for such a system, it's very easy to predict the output response. Essentially, it's given by this compact expression. This is a state transition formula for linear systems adopted to the case when the command is constant, so it's just equal to v for all times. What we can do now is to define the set O infinity tilde as a set of all pairs of commands and initial states that satisfies these inequality conditions. And let me explain what they are. If you go by row, this corresponds to requirement that the output of the system satisfies the constraint. So the first row corresponds to the output at time 0. The second row corresponds to output at time 1. And you go all the way to a certain horizon T star. And the last row is interesting because this is a requirement that the steady state value of the output, that is the value at infinity, satisfies the constraints, and it has to satisfy constraints strictly. Now, by doing that, you get a smaller set, so O infinity tilde is typically smaller than O infinity, but you can guarantee the existence of T star such that O infinity tilde is actually a strict subset of O infinity. And this is simply the reflection of the fact that if the constraints are satisfied over a sufficiently long horizon and they are strictly satisfied in steady state, then the constraints will be also satisfied for all times under the assumption of constant reference. Once you obtain O infinity tilde, you can eliminate redundant and almost redundant inequality constraints, while remaining constraints can be tightened to obtain a simply represented subset P of O infinity tilde that you can use in the implementation of the reference governor. This is how O infinity tilde looks for our first double integrator example. The full set is three-dimensional, and what I show here are cross sections of the set by constant V plane. So the meaning, for example, of the magenta set is that if I start anywhere in this set and I apply a command of -0.5, then the ensuing trajectory will satisfy the constraints. So in the case when the set P is a polytope, the computations of kappa of the scalar parameter is very simple because essentially it reduces to solving a system of linear inequalities, and kappa is a scalar parameter between 0 and 1. It has to satisfy the family of these linear inequalities, and the solution of this is trivial. In fact, most of the cases, kappa is equal to kappa u, which is given by this explicit formula. So you can estimate, for example, the number of flops such computations can take, as well as the implementation of this can be done in a very simple way. Now, this slide illustrates the impact of almost redundant constraint elimination on the computational complexity. This example is for a practical system. It's a fuel cell with about 10 states. So O infinity tilde here is in 11-dimensional space. And here's what we do when we eliminate almost redundant constraint. If you look at O infinity tilde, which is shown here by the solid black line, what we often find is that many faces are very similar, so the normals are pretty much close to being the same. In such a case, we can eliminate some of the inequalities in the definition of O infinity tilde, and by doing so, that are almost redundant, and by doing so, we obtain a slightly larger set, which is shown here by the magenta dashed line. What we can do next is to pull in this magenta set to get a light blue set here, which is strictly inside O infinity tilde. And after this pull-in, we can use the resulting set as our P in implementation of the reference governor. And as experience with several case studies shows, including for the fuel cell, the number of flops at each time step that you need to use can be reduced by an order of magnitude, with reasonable degradation in performance of the reference governor. Okay, so this begs the question, how general can the sets P be used in a reference governor implementation, and especially if you start looking also at nonlinear systems. And it turns out the sets can be quite general. They basically have to satisfy two properties. And the first property is safety, and the second property is a strong returnability. And safety means that if you start in a set, then the ensuing trajectories will satisfy the constraints for all future times. The property of strong returnability means that the trajectories that start in a set may leave the set, but they must eventually enter the interior of the set. So we do not require the invariance of such sets, but we do require strong returnability of the sets. And it's also helpful when the set P can be written as a sub-level set of a certain function V tilde, which is continuous, and you can certainly do it in the case of when the set P is a polytope, and in other cases when, for instance, you have a Lyapunov function, the easy way to generate this function V tilde is to essentially scale it by an appropriate amount, so that it fits inside the infinity. This is the reference governor that uses functional description of the set P in terms of this function V tilde. So again, it's a scalar optimization problem that you have to solve, subject to the constraint that kappa is between 0 and 1, and then this function V tilde has to be less than or equal than 0. And in some cases, the solution would be explicit. In other cases, you might have to do bisections on kappa to find the kappa that solves this optimization problem. Now, for a number of technical reasons, there is a small modification that's needed. That is, you accept small increments in the reference governor output only if V tilde is less than or equal than minus epsilon. In this condition, it's a technical condition, and it guarantees the finite time convergence to constant steady-state admissible references that I'll talk about next. But it's needed for that reason. Okay. Now, what if you don't want to compute this set P and you still want to implement the reference governor? Well, it turns out that you can implement it without computing P explicitly. What you can do instead is to use the online prediction of a sufficiently long horizon to determine if a given command and state pair is safe. The advantage of this online approach is that the reference governor would be reconfigurable to model and constrain changes. So if your model changes online, you just use the new model for prediction. The drawback of this approach is that the constraint reduction techniques that I have mentioned are not straightforward to use. Of course, it's possible to combine offline and online approaches together. That is to pre-compute P or infinity for part of the constraints, and then use the simulations to basically for the other part of the constraints that, for example, may be changing dynamically. Let me show some of the details for the response prediction based on base reference governor. Again, the ideas are simplest and the computations are easiest when the model is linear, because for a linear model, predicting the response to a constant command, it's pretty simple, given by state transition formula, adopted to the case of constant command, and you can write it essentially as a linear function in kappa. And so this is an algorithm that applies to linear models, and constraints do not necessarily have to be linear in this case. They can be nonlinear, provided that the set Y is convex. And what you basically do is that you, at each time instant, you set kappa equal to 0, and tau here is the running time over the prediction horizon. And you march along the prediction horizon, and you check whether the constraints are satisfied. If the constraints hold, you keep marching on. If at some time instant you find that the constraint is violated, then you tighten kappa, so you find kappa prime in the interval between 0 and kappa, such that the constraints hold. Then you assign kappa equal to kappa prime, and you continue this process till you reach the end of your prediction horizon. And what we find in typical case studies that the number of these kappa tightening steps, that is, you do something else rather than just checking constraints, it's actually very small over the prediction horizon. So this is an example of spacecraft relative motion control example where constraints happen to be quadratic and linear. They are convex. And as we control the motion of the spacecraft, on average, we do two times of tightening kappa. At maximum, we do six times when the prediction horizon is equal to 50 steps here. So it's an effective approach. All right. Now that I gave you a flavor how a reference governor is constructed and how it's functioning, let me tell you a little bit about existing theory, and that summarizes several theoretical results available in the literature. So first, linear and nonlinear systems with set bounded disturbances and parameter uncertainties can be treated. Feasibility at initial time implies constraint adherence for all future times. So this is a recursive feasibility property similar to the one in model predictive control. The other property is the finite time convergence of the reference governor output to the command or to nearest steady state feasible value, provided that the command is constant. So for constant commands, we converge in finite time. It turns out that similar convergence results can be shown for nearly constant and slowly varying commands under suitable assumptions. And finally, such schemes provide enlarged constraint domain of attraction compared, for instance, to feeding the command to the closed loop system directly. Okay. Now, the scheme that I've shown is the simplest kind of reference governor that works. And over the years, there have been numerous extensions of these schemes developed, and I tried to create an incomplete list of different designs and different ideas, and perhaps I can make a few brief comments on them. So if you look at vector reference governors and command governors, they do away with the assumption that we use a scalar kappa. So in the command governor case, we can directly minimize the difference between V and R, say the 2 norm squared, and typically you obtain a quadratic programming problem that you would need to solve to be able to find a solution. In extended command governor designs, we do away with the assumption that V stays constant over prediction horizon. V can be generated by an auxiliary system that is chosen as a part of the design process. Robust reference governors deal with parametric uncertainties and also with disturbance inputs. It turns out that it's relatively easy to couple reference governors with observers, in particular Leuenberger observers and set membership observers. So you can design the schemes based only on output measurements. Reduced order reference governors permit reference governor design to be based on reduced order models, while guaranteeing rigorously that the constraints are also enforced for the high order models. Nonlinear reference governor designs address, as the name suggests, the case of nonlinear systems. Incremental reference governors distribute reference governor updates over time. So the idea is that at each time step, you pretty much try to change the reference a little bit. And if they change the reference to satisfy the constraints, you switch to it. Otherwise, you stay at the original reference. Explicit reference governors, it's a very nice idea which do not use optimization at all. But they essentially use a feedback law design in continuous time, and by doing so, they guarantee traditional properties of the reference governors. You can develop explicit reference governors for time delay systems. Reference governors can also be applied to systems where the delay may be random or there are data drops, and this is the case for network systems control over networks. With some modifications, you can design reference governors for enforcing time-varying constraints. There is a way to do distributed reference governors. In-a-loop reference governors use ideas from passivity in order to be able to place the reference governor not outside of the nominal feedback loop, but actually inside the feedback loop, and that sometimes is useful in applications. You can design reference governors for models in implicit form, for periodic systems, and also for some classes of stochastic systems. Well, those are reference governors, and why stop on just modifying the references? With the same idea of augmenting but not replacing, you can try to govern other parameters in the closed loop system, for example, gains of the controller, and that's what parameter governors do. Virtual state governors control the state in reference governors. They also reset the states, and it's also possible to combine a reference governor and MPC schemes. I put 3 dots here because while this list is clearly long, it's not exhaustive of different ideas that have been proposed. And if you like to read a little bit more about reference and command governors, both in terms of their theory and applications, my colleagues Emanuele Garoni, Stefano Di Cairana, and myself, we have recently developed a survey paper in Automatica that it's a survey and also a tutorial paper that goes in details into some of this more advanced reference governors as well as into their applications. In the remaining time that I have, I would like to tell you a little bit about a few more recent applications that my colleagues and I have worked on, as well as a few more recent theoretical ideas that we have pursued. And I'll start with applications, and this is an application to an automotive engine. It's a turbocharged engine, a gasoline engine, in which one of the key constraints is to avoid the compressor surge. And to avoid the compressor surge, you have to maintain the engine trajectory on the compressor flow and compressor pressure ratio map below the so-called surge line. So you would like to be in this lower right corner. Now, for this case, there are 2 possible positions where the reference governor can be placed. It can be placed to modify the throttle position command, and this is the inner loop reference governor, or it can be placed outside and modify the air charge command that is fed to the air charge control of the engine. And as our vehicle experiments show, by applying the reference governor, you are able to mitigate the compressor surge constraint violation. These are real vehicle results. Now here's another recent application that we looked at to vehicle dynamics, and here what we are trying to do is to prevent the vehicle from rolling over. And the first scheme we have considered involves modifying the vehicle steering so that the driver provides some steering command, and assuming that we have an active front steering system, we modify it and we try to do minimal modification in such a way as to avoid the vehicle rolling over. So here's a small short movie that my colleagues and I have come up with that illustrates the operation of the reference governor. This is based on car sim simulations on nonlinear model, and without the reference governor, the vehicle rolls over. And now with the reference governor, we are able to avoid vehicle from rolling over in this nonlinear simulations. And I should also point out that if you look at the vehicle trajectory on XY plane, the modifications of trajectory is fairly minimal, but the rollover is avoided. You can extend this idea to coordinated use of active steering and differential braking. In this case, the reference governor is not flexible enough to handle the differential braking, and the extended command governor provides a good solution in this case that we've also developed fairly recently. Now, here's an interesting example where constraint control in general, and perhaps reference governors in particular, can be an enabling technology for future engines. These are examples of free-piston engines and free-piston engine generators for hydraulic and electric hybrid vehicles. In conventional engine, there is a mechanical crankshaft that constrains the motion of the piston and, for example, helps to avoid the collision of the piston with the cylinder head. But in a free piston engine, there is no crankshaft. And so you have to rely on control and basically on a software solution to ensure that the piston does not collide with the cylinder head. And so for this application, we've looked at applications of reference governors to govern the load that we draw from the engine, which is possible to do in hybrid vehicle applications, and to avoid this type of collisions. Now, one interesting aspect of this application to free piston engines is the fact that the model is based on energy balance and is given in implicit form. So this is a nice application of reference governor ideas for models that are formulated in implicit form and not in explicit form. Now, going from some automotive case studies that we have done more to aerospace applications, this is the case of spacecraft relative motion control, where we apply extended command governor on top of linear quadratic control law in order to avoid constraints on thrust limits, but also obstacle avoidance limits. And what we try to do here, we are trying to do in-orbital track maneuver of about 5 kilometers. And to perform a maneuver, an efficient maneuver in space, typically you have to go to high orbit and then descend down. What happens during the maneuver is that the spacecraft discovers that there is an obstacle that it must avoid. And so we separate the obstacle from the spacecraft by rotating hyperplane approach and essentially govern the motion towards the target without violating this constraint. And we develop both model predictive control solutions and LQ plus extended command governor solutions. And at least in our implementation, the ECG-based implementation was faster, and the trajectories that we obtained were fairly similar. This is another case study where we employ the extended command governor for asteroid lensing. And here we use a rotating hyperplane constraint that is shown here to separate the asteroid from the spacecraft. This this circle here shows the output of the extended command governor, that is the set point or waypoint which is given to the spacecraft. And then near lensing, we impose a pyramid constraint, and this is done on top of LQ inner loop controller plus disturbance input observer to do a bit of compensation for uncertainty in the gravitational field of the asteroid. And in simulations, nonlinear simulations, we are able to accomplish this type of lensing. So hopefully this gives some ideas about a range of recent practically oriented case studies that we have done. And then I'd like to mention a few recent ideas that we looked at, more on the theoretical side, even though strongly motivated by applications. And one of such ideas is the control state and reference governor. One observations we have made that often the nominal controller in our system is not static, but it's actually dynamic. For instance, it may include integral action and integrator states. Now, unlike the planned states, the controller states are under our control. So in particular, we can reset them if we like. And this idea of resetting the controller states, it has previously been used to increase the speed of convergence during stabilization. Essentially, you use controller state reset to dump the closed loop energy. But in our case, we use this reset mechanism of the controller states in order to enforce the constraints. Now, in this particular case, with controller state reset, the problem is more complex than the one of just a scalar reference governor. You have to solve an appropriately formulated quadratic program subject to the same type of constraints in order to determine both the command and the integrator state. And what's interesting that in some examples we find that this controller state and reference governor idea can be quite interesting and effective. For instance, if you look at sets of recoverable states for, say, gas turbine engine, this is based on a second order model where the faster dynamics have been removed, so we just have the speed dynamics in the model. But nevertheless, if I look at the sets of recoverable states that can be recovered by controller state and reference governor, that is, I can start at any of these states and without violating the constraints or continue to operate, then this set can be enlarged quite a bit by including the ability to reset the integrator state in this particular example. So that's an interesting idea, and here are some simulation plots that I'll probably skip. They basically show that the constraints are enforced. I should point out that these developments were based on linear models, so there is some degree of extrapolation involved, but nevertheless, it's still interesting. And what we've done a little bit more recently is to incorporate the ideas of CSRG into envelope-aware flight management system for the aircraft. And the idea for example, aircraft flight planning, that we decide on a sequence of trim point to trim point transitions. And so we can decide on that feasibility of transitions between two trim points based on a set of states that can be recovered by controller state and reference governor. And so here's an example where we have different trim points in terms of flight path angle and velocity of the aircraft. And then for the nominal controller, there is only a few transitions that are feasible, that is without violating the constraints. And with controller state and reference governor, there's many more transitions that can be done. And in this scheme, the actual transitions are controlled by using controller state and reference governor. Okay, so here is another development where we try to generalize reference governor to the case of systems with chance constraints. So this is a stochastic setting. And the motivation here came from practical applications to aircraft and also to flying wind turbines that are used for energy generation. The idea here is that such systems operate in wind environment, and so there is turbulence and wind gusts. And there are models, well-accepted models developed for modeling turbulence and wind gust. For example, von Karman model and Dryden's model, and these models are stochastic. And so the basic setting, if you work with linearized models, is this: you have a linear discrete time system, but there is an additional disturbance input, which is stochastic. Here, and you're trying to enforce constraints, for example, on angle of attack, tether tensions in case of a flying wind turbine, and so on and so forth. Now, in such a setting, it's not possible to satisfy constraints for all times simply because the disturbance doesn't have a compact support, and so eventually the constraints will be violated. So what you can do instead is to impose a chance constraint, which is to require that the probability of the constraint violation, say over the prediction horizon, is greater or equal than beta. So essentially you are requiring that the measure of trajectories that violate the constraints is sufficiently small, and the probability of the one satisfying the constraints is greater or equal than beta. Now, another complication in this setting is the fact that you cannot really guarantee recursive feasibility with respect to even this chance constraint, because if disturbance is large, it will cause the state to go away to very large values, and of course, this constraint may no longer be feasible. So the infeasibility handling mechanism is very simple in the reference governor case. We simply set kappa equal to 0, and that maintains the reference constant. So if we cannot satisfy our chance constraint, we do that. And what we are able to show for the closed loop system, that is with this infeasibility handling mechanisms, is that the probability of constraint satisfaction is greater or equal than beta for all the future times, so it's consistent with our design intent. And also the probability of our reference converging to the reference governor output converging to our reference in the case of constant references in finite time is equal to 1. So essentially we recover the property of the deterministic reference governor in such a case. Okay, and then here is another situation where we apply reference governor ideas to formation control. In this particular case, this is to spacecraft relative motion control, where we have multiple spacecraft and we are trying to build a formation without violating constraints, including collisions between the spacecraft. And there are two ideas here, time shift governor and the scale shift governor. And the movie I show here is for the scale shift governor. And the basic idea here is that we perform coordinated adjustment of reference commands to multiple vehicles to ensure that the constraints are satisfied and we reach the desired relative motions in this case. Okay, and this actually brings me to my last slide, the last slide of my presentation, where I'd like to make some concluding remarks on reference governor. So the basic idea that, or the basic situation that the reference governor addresses is when you have a nominal controller designed and you're pretty happy with this nominal controller and perhaps you don't want to redesign it, but you'd like to augment it with something that will take care of constraint violations. And one such scheme would be the reference governor. So it augments rather than replaces the nominal controller. And that's what reference governor does. It modifies the reference commands. And as I've shown, you could also perhaps modify other closed loop signals. Reference governor enforces constraints, and it is inactive if there is no danger of constraint violation. It's something that can be designed and structured that is easy to implement and has a relatively low computational footprint. It has special and desirable response properties, such as finite time convergence and staying inactive for constraints that are well constrained admissible. And finally, there is many opportunities for future research as well as applications of these ideas. And in terms of research, I can certainly mention one topic which involves fusing reference governors and adaptive systems, that is using reference governors on top of either adaptive or learning systems, as well as applications to very high order systems as well. It's an interesting research area. There are more discussions of additional research directions in our survey paper, and of course there is quite a few different opportunities for applications. And that concludes my talk, and thank you very much for your attention.
Thank you very much, Ilya. So, Ilya, if you like, I can start reading questions.
Okay.
So, just a second. I am trying to see my chat box. Emre, how can I see it better? Okay, I will try to read it. It is a bit small one. Okay, so a question from Ehsan Arabi. He says, thank you, Dr. Kolmanovsky, for the great talk. My question is about handling system uncertainties. Having system uncertainties, it seems that we cannot obtain the set P based on initial conditions and the inputs. Does this also fall under the online approach you mentioned without requiring computation of P?
Mm-hmm. Yes, that's a very good question. And in what I have described, I have not discussed how reference governor handles, for example, set-bounded disturbances, as well as parametric uncertainties. Our survey paper has some details and some references to papers where this type of ideas are being discussed. So I didn't go into those details just to avoid unnecessary technical complications, but there exist tools for handling the parametric uncertainties and perhaps better developed tools for handling bounded disturbance inputs with the reference governors.
Thanks a lot. Another question from Reza Amini. He says, would you please ask Prof. Kolmanovsky to make few comments on the combination of RG with MPC scheme and also RG with other tracking controller techniques. I also wonder if an online technique is used to optimize the RG gain compared to MPC, which one is faster?
Well, those are good questions. And I should point out that once again, the survey paper that we have written has a section that discusses connections and connections between reference governors and model predictive control in more detail. And so there are a few points in a survey paper. But let me suggest one potential use of reference governors together with model predictive control. Often in model predictive control, you use terminal set constraints in order to guarantee recursive feasibility and stability of the closed loop system. And in case where you have reference commands or reference set points, this terminal set is centered around your set point. Now imagine you have a very fast set point change, and your MPC controller uses short horizon. Then at the moment when there is this very fast set point change occurs, you may lose feasibility because you cannot satisfy the new terminal set constraint. Again, this is just one idea that where a reference governor can either implement it within the structure of model predictive controller or the standalone unit could potentially help. But there are others.
Thank you so much, Ilya. Reza says thank you. Okay, so can we say, I mean, there are two questions. If there are any questions, can online audience can email you?
Yes, absolutely. I'll be very happy to answer questions and interact more on these topics. Absolutely.
So Ilya, I would like to again thank you very much for your time and for your great talk. I also personally enjoyed your survey paper as well. Thanks a lot.
Thank you very, very much for the opportunity to give a presentation, and I enjoyed it very much as well.
Thank you. So basically, then with this, I am ending the session. And for everyone, I would like to thank Ilya, Dr. Kolmanovsky one more time. And for those who missed, also, Ilya, I am going to post your talk online. I will send you the link as well if you want to share with others too. And,
thank you very much.
And thank you so much.
Thank you.
Thank you. Have a great day, everyone.